So we did some more experiments. What you see here is a test where we compared salt brines that had a number of different high molecular weight polymer additives. And what you're looking at here is the plates after 2 hours of exposure to freezing precipitation in the W-set chamber. Plate A was treated with plain sodium chloride brine with no additives. And note that after 2 hours, we've got a large accumulation of that white rime ice. Compare that to the plates that were treated with salt brine that contained different polymer additives. Particularly plate B, E, and F. Notice that after 2 hours, there's essentially no white rime ice at all. So this is interesting. We've shown that there are additives that will inhibit the transition in what's going on with the way the precipitation is interacting with the de-icer. It will inhibit the transition at which that white rime ice forms. And it raises the question, does this indicate a way that we can measure the relative effective lifetimes of de-icers? Now, this is admittedly preliminary research. Further investigation would need to be done if we think this is interesting to try and understand to what extent we can actually relate this to what's actually going on in the field. But I think at least it tells us some interesting things about how de-icers respond to the continual exposure to freezing precipitation over time. All right, now with the last amount of time that we've got this morning, I want to circle back and talk about some things that we've learned from those initial ice melting capacity experiments that I mentioned about how de-icers perform at very cold temperatures and about how we might perhaps improve the effectiveness of de-icers at cold temperatures. Now, the conventional wisdom, of course, is that salt is ineffective at temperatures below about 10 degrees, give or take. Whereas we all know that magnesium and calcium chloride are much more effective than salt at colder temperatures, at below 10 degrees Fahrenheit. The common explanation for this is given in terms of those basic measurements that I talked about at the very beginning, namely ice melting capacity and freezing point or eutectic temperature. The common explanation that's offered is that magnesium and calcium chloride have much lower eutectic temperatures, and they do. Salt's got a eutectic of minus 6, mag chloride's got minus 27, calcium chloride's way down there at minus 60. So because they have lower eutectic temperatures, they are said to have higher ice melting capacity at cold temperature, and therefore they work better. Well, we wanted to understand better what was actually going on here. So we took that test method approach I described at the beginning. So that's why I dragged you through that explanation, so you'd understand the testing approach we were using. We took that testing approach so we could make some accurate and precise measurements of the ice melting of salt, mag chloride, and calcium chloride at cold temperatures to better understand what was going on. And we saw some interesting things. This graph shows you the ice melting at minus 4 Fahrenheit of salt versus mag chloride versus calcium chloride. Why did we choose minus 4? We chose minus 4 because I wanted to get as close to the eutectic temperature of salt as possible. Now, the eutectic temperature, that is the number that does set the true bottom limit of ice melting. The ice melting capacity truly goes to 0 when you're below the eutectic temperature. It's impossible for a chemical to melt ice below the eutectic temperature. So I wanted to get as close to minus 6 as possible to have a worst case scenario. I wanted to see how much melt will salt give me under very cold conditions where I might expect any melt at all. Well, this is what we saw. And I should also point out, this is compared against mag chloride flake and calcium chloride flake. Note that both mag chloride and calcium chloride contain waters of hydration within the chemical, and I subtracted the contribution from the waters of hydration from these melt values. So what you're looking at here is the melting of the ice melting per anhydrous chemical, per actual pure chemical. So this is what we see. If we look at 1 hour, we see the conventional picture that we're all used to. At 1 hour, there's basically 0 melting from salt, very little. not zero, but low. Whereas we have substantial melt from magnesium and calcium chloride. Okay, that's just what we're used to. And again, that's what the SHRP method suggests, making measurements after an hour. We commonly make measurements after an hour for a good reason. We often want to know what kind of effectiveness we're going to have in a short period of time. But for the purposes of understanding better what's going on, it is instructive to look at what happens at longer times. So this is what we see. Note that as time goes by, salt starts melting more and more and more. If I wait for 24 hours, salt melts more ice than mag chloride does per pound of chemical. If I wait 48 hours, salt melts substantially more ice per pound than either calcium chloride or magnesium chloride, than either of our conventional low temperature ice melting chemicals. This gives us a number of very interesting conclusions.